Okay, fallback. Okay, Dr. Ahmed.
Yes, so let's go ahead and.
You want to introduce? I think everybody knows everybody except I think.
Yeah, except Elizabeth. Yeah, Elizabeth. She's also joined us late. Early last year, and she has been working on the economics part. So her main work is, like techno-economic analysis of the BRO system. And she's in her second year now of her master's, and so she's a new member in the team.
Welcome, Elizabeth.
Thank you so much.
Team. All right, so we go back to you. Do you look at all the photos? If anybody on the photos you don't know, point them out and let them introduce themselves. Otherwise, we could.
Okay, I don't know Joel, Ralph. I'm not really sure. I know you very much.
Okay.
Sean, yeah, and Darren.
Oh my God, they don't know anybody.
So we need to go through a full introduction, just a quick one maybe.
All right, I'm Samer Adham. I'm the manager of the Water Center here in Doha with ConocoPhillips.
Okay.
Yeah. And I'm Joel. I'm an engineer at the Water Center as well. So we work in different projects, membrane technology, absorption, and things like that. So we're part of the Water Center, so Doha.
Okay.
And I'm Dareen. I'm also an engineer here at the Water Center, and I'm an Aggie. I'm a graduate of the master's program with Dr. Ahmed as well. So, and I think, Elizabeth, we saw you only once in the QNRF progress meeting that was early last year. You were still new then. But,
okay.
Yeah.
And we have Mashal with us. You probably don't say, but Mashal, you want to introduce yourself?
Yes. I actually also met her during the progress meeting. So I'm Mashal. I'm an engineer at the GWSC, a chemical engineer. My degree was from Qatar University.
Nice to meet you.
Yeah, and on the other side, we have Dr. Sean joining us from the University of Technology in Sydney, and Ralph Mendales also. He's joining from the University of Technology Sydney. Dr. Sean, he's also a member of the PI. He's a PI on the project. And Ralph also has been working on the project for the last 3 years.
I want to know, Ralph, are you a PhD student? Are you a postdoc? I don't know. What's your affiliation with the university or something? Yeah.
I just finished my PhD, and I'm currently working here at Kobe University in Japan.
Oh, good. Congratulations.
Yeah,
that's
good.
That's great. So I think we can go ahead and start. As suggested by Dr. Samer, is like for each team to have like about 10 minutes of presentation about the progress during the last period or during the last year, and then we can discuss the way forward as well. The project was officially supposed to expire last January, and we requested for extension until October. And part of the reason is because again there was some kind of delays in some aspects, and due to some experimental challenges, and also some delays related to the COVID-19. The main, also one of the main reasons as well is because that this project we have matching funds coming from QNRF, and the rule related to the matching funds is that QNRF does not pay us the money until we spend 75% of the original funds of the project. And this has delayed the transfer of the matching funds from QNRF they transfer it year by year. So for the second year, we just got it, I think, a few weeks ago, and then the third year we haven't gotten anything yet from QNRF. So we might also request additional extension, as I was discussing with Dr. Samer, but we will make sure that this does not affect any future submissions. We already missed the cycle 14 of submissions, but hopefully, for sure, this will not affect the future submission.
So there is funding for 1 more year there, basically. If we haven't gotten the funding for year 3, we have been funding for
that's in terms of, the matching funds, which is still
the matching fund. Yeah, okay, only the matching fund. Okay, yes.
And
okay, so
Doctor, go ahead, Dr. Ahmed. Yes, this is good.
Go ahead.
No, I was wondering. You're right. I mean, it's those are the challenges of the fund transfer in a way. But so today we will see how much of the scope have we finished in a way, and how much, if there is anything else, because if anything, it impacted. Did that impact money being sent to Australia as well? With that, I mean, because for us it's all in-kind contribution, as you know. But
right.
did that impacted transfer of money to Australia or not?
It hasn't, and Dr. Shun can confirm that. It's because the majority of the matching funds are utilized at the time of field. So that's the Sydney funds. Basically, they're mainly from the QNRF, original QNRF funds, and we put most of the matching funds in the time of field bars, because also I was worried about what's going to happen with these funds. So yes, the collaborating institutes were not affected. The affected institution is mainly Tamil. So I think I can start to give a brief kind of introduction about, to just remind everybody what the objectives of the project is, and I will go very quickly through what we have done at TAMU, and then we can go through the Okay, so basically, to just remind everybody that the objectives of the project was mainly to develop multi-layer thin film composite membranes with dense layers, and the main idea is to basically manufacture membranes that can withstand high pressure and also are suitable for the produced water in terms of fouling and stuff, and to investigate reducing the membrane fouling using functionalized nanomaterials. Evaluate and optimize the membrane performance in VRO system by doing basically the VRO experiments using synthetic and actual produced water. Develop optimum configuration and operating conditions for the VRO system. Conduct techno-economic analysis and basically develop knowledge and problem-solving capacity. So this was the 6 or the 7 general objectives for the work. And the first, in terms of technical approach, the first task was to develop experimental and analytical procedure by setting up the test units, by also demonstrating the analytical procedures for the produced water analysis and treatment and so on. And then the VRO membrane design and fabrication, and basically to fabricate and optimize membrane support layer, and also modify the membrane bottom surface to enhance anti-fouling, and synthesize basically the polyamide selective layer on nanofibrous support. And this was mainly the Sydney contribution. And then to evaluate also the performance of the VRO system, which is also distributed among the 3 institutes. And part of it is to acquire actual produced water and prepare model synthetic oil water, which also done. Evaluate effects of water composition and operating parameters in VRO membranes, the performance, pre-treat the VRO source water. And then the 4th task is to system modeling and optimization, is to develop mathematical model for the VRO process that accounts also for the dilution effects without using empirical equations. And then find the optimized or the optimum configurations for the VRO system, and do the techno-economic analysis based on that, and also to develop design models that can be used to scale up the VRO unit. This was the main kind of tasks that we had for the project. These are basically the test units at ThermoQ and also at ConocoPhillips. I don't want to go through them in details. But, you know, like for the experimental part that we have done at ThermoQ, there were some challenges, and Khaled will talk about them briefly. I will just go very quickly through the modeling effort, especially the latest progress. As you know, we have basically developed the model in order to be able to expand this to full scale planet, and the main issue was the dilution effects, because everybody has been using empirical equations that did not account for the dilution effects because they were based on the batch kind of scale or the lab scale units. And the main idea is to, instead of using like kind of, you know, like an equation that assume everything is ideal, or empirical equation like Van Hoff equation, is to use mainly a sophisticated equation of a state that basically it's easy to use when you account for the dilution effects, and also at the same time it provides you an accurate predictions, especially for the osmotic pressure, and also to combine the mass transport and the thermodynamics as well when you model the BRO system. And this gives you just kind of, you know, the comparison between the salinities predicted by the equation of state and the empirical equation. You can see that the equation of state actually very accurately predicted the experimental data. And then we developed also, you know, like the process to account for the dilution effects, which we discretized the membrane into slices, and each slice was considered as one membrane by itself in order to account for the effect of the dilution as you go through the membrane area for full scale. This will not make a difference when you talk about lab scale, but for full scale it makes a big difference as such. And after we did that, we validated the results. As you can see here, that actually the model predictions actually fits the experimental data very well, and also some of the data that were developed at the Global Water Sustainability Center was also fitted using the model, and I think there was a very good agreement between the experimental data and the model predictions as well. We also extended this to the full scale after we discretized, and then this shows also the difference between when you use the Van Hoff empirical equation and you use the model using the equation of state. You know, there is a difference in the specific energy, and also there was a difference in the power density as well. And then we accounted for the flow regimes in terms of co-current and counter-current flow, and what is the effect of both, also the function of the membrane area. And then we optimized the system by basically incorporating the quota optimization tool to see what is the optimum configuration of the system and to be able to find the optimum operating conditions. And this has applied also to, for example, this shows the specific energy and power density together versus the area, and then it tells you what is the optimum here that achieves both optimum specific energy and power density at the same time. We extended also this to the spiral one because that's what usually is implemented in reality. And also the same thing, we did discretizing and also slicing the membranes to also simulate the flow regimes. And this also, we validated the model using also experimental data from the lab scale. We also compared the spiral one with both the co-current and the counter-current flows. So the red one, the spiral one, and then the counter-current is the blue one, the black one is the co-current. And this, you can see that the spiral one performance in terms of water flux and power density, it's between the co-current and counter-current, and that's actually expected. And then this also, the model was able also to predict the concentration profile along the membrane, as you can see it here. So this is for the feed, the right side for the feed flow, and the left side is for the draw flow. So that's also was a nice thing that was done by the So that's just a very quick summary, and then I can transfer to Khalid, but also we can transfer to either Sydney or Konoko, Phillips to present the part, and then Khalid can come later to talk about, because what Khalid is going to talk about mainly some of the challenges that we face in terms of experimental work. So what do you suggest, Dr. Salim?
Yeah.
Yes, I'm happy.
Maybe, I mean, it's I have a couple of questions about the modeling. So is there any more modeling that you need to do, or for what the project is? Or I think, are we complete on this? I mean, I know Sally have just published. Yeah.
Right. Yeah, that's a very good question. So yeah, for the modeling, I think what is remaining is mainly the techno-economic analysis. It's not related to, it is related in a way to the thermodynamic and mass transport model, but in order to expand the model to use what we have done and also account for the techno-economics of the system. So that's what Elizabeth is doing now, and she's developing, she has already developed some cost models for different equipment, and also for the membrane system, which includes also pre-treatment costs, construction costs, capital in terms of also membrane costs and pumping, turbines, and all of these kind of things. And she's actually putting all of this together, and this will be incorporated in the overall model. So the model also can predict the cost based on the input parameters, like how much water you want use per day, how and the power density. Yeah.
So that's important, actually. The technical, and you're right. Actually, I was reviewing the whole work package because I was wondering really what are remaining on the project. I think so that's one item remaining, which actually aligned with and that's aligned to you and to Dr. Marcio at the time with Elizabeth right now. So that's in the work right now. I have a feeling, Dr. Khalid, challenges is stuff that we have experienced last year, and I'm just wondering if maybe Dareen should really, because we really, look, this is not an easy project to do. So Dareen maybe can, and you could ask her some question and maybe could answer some of your challenges that you have. Your call, I mean, Dr. Ahmed. But
I'm totally ready for any show. Did you call?
So, but I do know, because even Dareen was coming to me, even Ramadan is coming, and to tell me how long the experiment is. But also we had the specific challenges last year that we really had to go back, and even we lost some data and that stuff. But anyways,
maybe we can do it online with each other. So once we come to the challenges with the experimental parts, we can do it at the same stage. Maybe.
No, I think she's almost finished right now. I think so that's why I want to show you where Dareen is. Maybe Dareen can take 10 minutes to tell you where she
start.
And then I follow.
Sure. Yeah, I think let's show you where Dareen is, because you will know where she is, and then we'll move to Dr. Ahmed, and then we will see if your challenges have been addressed or maybe there are different. Okay. But one final thing, actually, Dr. Ahmed, at the end, I was wondering, is there going to be a chance to have access to that simulator model that Hosnain have done, or I'm not sure if that will be an outcome of the project. It will be nice that we. Is the plan to release it to the public? Is that right? The simulator, is that?
We can at least we'll share it with you and have somebody from Konoko to be trained and be able to use it in his or her own. We can do this for sure, and we can do it anytime you wish, starting from now. We have Hosnain is gone. Sally, she's done also. She's number 3 now. But Elizabeth, she knows well how to use the model and how to actually. She's working on it now. She's updating it and including the techno-economic analysis, and she knows how to kind of use it to predict, power density and stuff like that. So so it is ready to
Great. This is a great Ramadan effect, Ramadan task. Actually, I will delegate it to Dareen and Masha'il with Elizabeth to have that exchange. That would be good, and they could do it virtually. But Dareen and Masha'il, and Joel, if you whoever is in, let's do it. Dareen and Masha'il initially, and then Dareen and Masha'il will transfer the knowledge within our GWC.
No.
So Dareen, yours. I think my question actually, just to start here, is that for us, I really was my objective. Thanks everybody, just to see where we are, because I want to know what is remaining from the project, that we complete the task actually, and like you said, Dr. Ahmed, it is a challenging project without a doubt. At the same time, we need to make sure that we don't extend it too long, that it impact our next cycle in a way. I think you and I are limited on that. It's extremely restricted. Yeah. And also, I don't really know the reputation of the team in a way with QNRF. I don't know. Do they value? Do they say that, oh, those projects have lasted 5-6 years? I mean, you want to be one of the people who, yeah.
Right. Yeah. For us, I think we look good with the QNRF. I mean, after the meeting with Dr. Omar Bukharis from QNRF, during the review meeting, he was very pleased actually with what we're doing, and he knows that we are doing. It's a big team, and also the effort that is being put on the project is more than what we asked QNRF for. In terms of resources that we are actually with. In terms of progress, I think for us, it's not for QNRF. I think for us, there was something that we were, or some stuff that we were hoping to do, and actually we didn't have a chance to do it. Like, for example, working at high pressure and being able to basically do the high pressure that responds to the high salinity of the produced water. And that's where we faced the challenges, and we were not able to do that, because that was the main kind of idea, is to be able to recover more power and more energy by expanding the pressure range that you can actually implement the membrane. And this was like kind of a challenging for both actually the units that we have and the setup that we have. When you apply to high pressure, there was some challenges in the feed stream and also in the draw stream that Khaled and I think Dareen also talked about.
We'll have it. Yeah.
And the other challenge was also the membranes, and in terms of how they can handle pressure. So that was the thing that we were like kind of but I think with because we published a good amount of papers, and we basically showed good also collaborative kind of effort in a way to QNRF. So I think, as far as I'm kind of I know that we are fine in terms of QNRF reporting. Yeah, we don't have.
We have done, actually, don't worry about. I mean, I think we need just to tell them what we have done in a way, and that will be plenty. Okay. I mean, yeah, there is in every project what we have not done in a way, but I mean, they're not. We have done so much actually that if you just say it by itself without really listing what you have not done, they will be proud. Okay, I think that's fine. I think let's hear what I think. Then maybe some of the challenges of the Khaled is not. Yeah, some of them are ours. I think Dareen will discuss, but some probably he has new stuff. So let's go to Dareen 10 minutes very quickly of what our progress, and then we could hear what Australia, and then we all try to help Khaled.
Yes. So I'll start with a quick then summary of the work we've done the past year. Now we're used more to teams, so just. Is everyone seeing my screen to make sure before I start speaking?
Yes.
Okay. So in terms of the agenda for this quick presentation, so this was the last in-person meeting that we had, I think in April 2019, way before Corona and all of the travel restrictions. And
oh my God.
So hopefully we could maybe take a nice virtual photo at the end of this meeting, but yeah, that's something to remember.
Yeah.
For the agenda for this presentation, I will quickly highlight our pre-treatment evaluation, focusing on the actual produced water and how we've evaluated it in PRO fouling tests. We also have results on our hollow fiber membrane testing. And then finally, just a quick outline of how these results and deliverables then would be written in our final report, and some key project conclusions based on these aspects. So to start, you're all familiar that over the past 2 years, we've received and characterized approximately 3 produced water samples from different ConocoPhillips operations sites. And this table is just an overview of the general analytical properties of these produced water samples, covering pH, conductivity, and also the organic fraction. So in terms of TDS, the salinity varied between around 90,000 to up to 300,000, and this TDS is reported as the summation of ions that we measured through ion chromatography and inductively coupled plasma as well. So we can see that produced water 3 is much higher salinity, but produced water 1 and 2 also have quite high salinity with respect to oil produced water at around 90,000. In terms of the organic fraction, the main aspect that we were looking at was the total organic carbon, which was the highest for produced water 1 at 500 milligram per liter, and then both produced water 2 and 3 were around 100 milligram per liter of TOC. So based on this water quality, we evaluated different pre-treatment technologies targeting the removal of mainly the organics and the suspended solids in the produced water to enable its use as a draw solution for our PRO evaluations and to minimize membrane fouling as much as possible. So we evaluated 3 pre-treatment routes and defined them as extensive, intermediate, and minimal. Each was a combination of physicochemical and physical treatment technologies, including dissolved air flotation or DAF, which includes a coagulant. We use mainly iron chloride as the representative coagulant, and followed by cartridge filtration, either 1 micron for the extensive and the intermediate, or 10 micron for the minimal pretreatment. The extensive route also included a final polishing step, which we added powdered activated carbon, PAC, and microfiltration as an additional pretreatment step. So we applied these 3 pretreatment schemes on the different produced waters, and as an example of the type of water quality for produced water 3, this is just a summary table of the percentage removals in terms of turbidity and TOC in the minimal, intermediate, and extensive pretreatment routes. Sorry, let me just get some water. So in terms of turbidity, the minimal pretreatment removed almost 87% of the turbidity, while intermediate and extensive removed all of the suspended solids and turbidity in the water. For TOC removal, that was slightly less because some of the organics are naturally dissolved in the water, and for the minimal pretreatment, we managed to remove 45% of the TOC, while the intermediate and extensive increased at 62 and 73 respectively. So that was the main analytical property that we were tracking in the water, and you can notice that there are slight differences in the pH and conductivity, which is mainly due to the pH adjustment during the DAF step and the dilution also, as we add the air saturated DI water during the bubbling stage of the dissolved air flotation. So with this produced water treatment summary, we kind of then took that pre-treated water and evaluated it in PRO fouling tests in order to see the effect that would have on the flux of the PRO membranes in PRO operation. And the next 2 slides just go through an overview, a high-level summary of the experimental protocol that we used. In this table, you'll see the parameters that were kept constant throughout the testing. The testing was mainly 5 stages. Some parameters were constant throughout, and in the next table you'll see on the next slide some of the parameters that were different for each step of the experiment. And our main objective again was to evaluate the effectiveness of then these pre-treatment routes in using them for produced water treatment as draw solution for PRO. So the membranes that we used for the testing were the Toray flat sheet TFC membranes, and the feed solution was kept constant as 35,000 milligram per liter NaCl, mimicking saline TFC water. And as you're aware, our focus here was first the pre-treatment of the produced water, since seawater pre-treatment is well known and well reported also in various literature. So we kept it kind of, in order to allow focusing on the produced water, we just used synthetic seawater at 35,000 milligram per liter on the feed. The pressure was, or the applied hydraulic pressure, was at around 14 to 15 bar for all of the stages. And the duration of each step to get like an average flux or normalized flux was 4 hours of runtime. And on the next slide, you'll see a slightly more complicated table, but it's actually quite simple. It's just the 5 different stages. Each was done on a separate day. And in each experiment, the draw solution was different. We obviously had to start with a baseline, which was the first baseline, where we used 215 gram per liter NaCl, mimicking the salinity of the produced water after pretreatment. And that was then done at the beginning and after each of the fouling experiments. The draw solution flow rate was always constant at 0.6 liters per minute. And then for the fouling steps, we used the actual produced water after pretreatment. And you can see that these blue bars are basically, we had rinsing of the unit with DI water and overnight compaction with DI water before each of the stages. And obviously the note here is that we included again the addition of biocide throughout all the experiments to avoid the formation of any biological matter that would foul the membrane or affect its performance. And then we had
learning actually.
Yeah.
Darine, I was suspecting, because it really took us, maybe Khalid, if you do 2 cycles or 3 cycles, if you don't have a biocide, you would start to have a funny data. So I was wondering if that has been experienced by Khalid, but it was experienced by our team, and we solved it. We end up finding that, yeah, if you need to do not 1 experiment, 2 of those, okay. So I suspected maybe Khalid have gone through it, but if not, just if you are going to do multiple cycles, you might need to just consider that. So that's one thing I thought of, a lesson that we really experienced. So Darine, continue, sorry.
Yes, correct, Dr. Simon. We had to discard like a portion of the data for the experiments without biocide because the flux would just become all over the place. The membrane would then be compromised, and that affected the performance, and we couldn't kind of get any conclusive answers from the test without a biocide. So,
Darine,
yes.
Darine, just a quick question. So, did the biocide affect the integrity of the membrane by any way? Because these are like kind of, we use polyurine, right?
We did keep a very low 5 ppm concentration of the biocide, and we kind of compared the baseline flux when you had only salt and when you had with biocide. It didn't affect the membrane's baseline performance.
And Dr. Ahmed, this biocide is being used for RO applications usually. So we got it. So if it does, it's a common biocide to be used in RO applications. So it does not impact reverse osmosis membranes. So there is no, okay. We thought it should not really impact the PRO membranes. Yeah.
It's tested on membrane, so it's for membrane basically. So a high pressure membrane.
Oh.
Also.
Yes.
Go ahead, Dylan.
And just the final aspect here for this table, we had the criteria if fouling was observed from the first cycle or after the second baseline, we would then obviously stop the evaluation, and there was no need to go through the second cycle and the third baseline, sorry. So based on that water quality and this PRO evaluation protocol, we then tested the minimal, intermediate, and extensive pre-treated waters on the PRO membranes. And in the first plot here, you'll see the normalized flux. So the flux for each stage was normalized against the moving average of the first baseline. So if we have a normalized flux of 1, that means we didn't see any fouling. If it decreases, then that directly correlates to the percentage fouling that is observed on the membrane. So when using the minimally pre-treated produced water on the TFC PRO membrane, you can see that the flux for the actual produced water stage went down to 0.8 normalized flux, so that's around 20% decrease. And then when doing the second baseline, which is only an NaCl solution, we noticed that the flux decreased by 60%, down to 0.4 of the original baseline flux. So there was clear fouling, and if you see, like while the experiment was running, the flux would just steeply decline by more than 60%. And after that, we even actually took out the membrane, and there was some brown and yellowish kind of organic matter that seemed to have deposited on the membrane, and it was clear fouling of the membrane in agreement with the flux data. So we went and tested the intermediate produced water on a fresh membrane coupon, and as you can see here, the normalized flux was stable at 1 for all of the first baseline, the actual produced water run, and the second baseline. And so we went further and tested the second actual produced water and the third baseline. It was all around 1 approximately for all of the stages. There was just some fluctuation in the second produced water run, but that was kind of recovered in the second baseline. So it could have been good pre-treatment, but not good enough to get like the perfect stable normalized flux. So again, we went with a new membrane coupon and tested the extensive pre-treatment, which includes the additional PAC and MF polishing steps. And here we got more of a smoother performance. And again, the baseline and actual produced water runs were all at 1 normalized flux for the entire experiment. And we did validate this for different membranes as well as the different water qualities. So we tested it on produced water too as well, and got different membranes, and got also a 1 normalized flux. So based on these results, you can see that there is no clear fouling that we've observed on a bench scale level after conducting 2 cycles and doing those on multiple membranes and different water qualities. So it indicates that these pre-treatment technologies are sufficient to pre-treat the produced water for use as draw solution on the bench scale level. And obviously further validation would need longer term testing at a pilot scale where other issues could come up. So here, like Dr. Samer said, we saw the biocide issue, and that affected the membrane. Longer term testing of more cycles could show other issues, but at this stage we can see that there was no decline in the baseline flux. The membrane performed stably in terms of pressure and in terms of flux throughout all of the stages. So
but
that
we are
was
hoping, Darine, that it will be the intermediate, where the extensive
Yes.
is too much, the minimal is too little. The intermediate is the one that we need to optimize, we think, and that could not be done in a pilot scale, better in a long-term pilot study or something. That's, as a recommendation for further study, because extensive, we don't want to look like we are unconsiderate, that it's really too much to put that much stuff of treatment. But the intermediate is reasonable, so that's what I'm saying. Darine, go ahead.
Yes. Yes, correct, Dr. Summers. So that was then the last slide about the pre-treatment or the flat sheet testing. We do have, again, a couple of slides on the hollow fiber PRO testing that we did, and I'll start with the experimental protocol. So this is based on our exchange of emails with Ralph later last year and Dr. Sean, as well as your published paper on the hollow fiber membranes and desalination. And just quickly, the experimental protocol, we started with a pre-membrane conditioning at around 10 bar for 30 minutes approximately. And the feed and draw solution were DI water and 1 molar NaCl, both at 150 ml per minute. The applied pressure here was slightly lower than the flat sheet, but we managed to operate at 10 bars and get stable flux as well. And the membrane area for the coupons as provided to us was 17.3 centimeters squared. So this is, again, a picture of the membranes of the last batch that we received and our bench scale system. And first of all, when comparing, again, thank you, Ralph and Dr. Sean. So you did provide us also with average flux data for the different coupons, and that was useful to us to compare our results and kind of get an idea whether we were performing as, or the membranes in the bench scale unit in this configuration was performing as expected. So in this plot, you can see here for around 35 minutes, the average flux for membrane 2, when we tested it, was around 12.2, and these the orange squared data represents the average flux obtained from the UTS testing on the same membrane, operated at around 9 to 10 bar. So we did get stable flux, and there was the salinity was also stable on both sides of the membrane. And we went ahead and kind of tested the PRO curve for the membrane and did the stepwise decrease of the pressure. And each point here represents an average of around 40 to 50 minutes of flux. And you can see that we do get like the PRO performance curve, but of course, since the pressure is quite limited, then we don't see the full performance. But this is also similar to the data published on this membrane in the recent paper also on hollow fibers by the team. So this is just our initial or our testing for that hollow fiber membrane, and we did get stable power density and flux data for those membranes. So as a summary then of these outcomes or different aspects on the pre-treatment and on the PRO evaluation system, how we see those results going into the final project based on the deliverables. Per work packages first, the one work package 2 related to developing analytical and experimental procedures, where we've demonstrated the performance of the bench scale unit at both flat sheet and hollow fiber modes, did the initial bench scale hydraulic testing, and also together with the team developed the experimental protocol. In terms of the work package 4 to evaluate the performance, then the actual produced water composition comes into the picture, and the recent results on identification and implementation of sufficient pre-treatment, as well as evaluating the effectiveness of this pre-treatment in PRO mode testing, in addition to the power density output and validation that we have against modeling from A&M, the work we did with Hosnain and Muaz as well earlier last year, in terms of the power density output and the power density also of these hollow fiber membranes. And finally, work package 7 would be then related to communicating these results, like you said, in several publications already that are as a result of this project, as well as others in the pipeline that would report the recent data. And with that outline, then this is the last slide that I'll present, is just the key conclusions then from our side of the testing, that yes, using hypersaline produced water is very promising in terms of the osmotic energy potential that it has. We're still limited in the pressure that we're still limited in the pressure that can be applied either due to the membranes and the unit operations as well. However, at the bench scale level, this data is sufficiently providing a proof of concept at this stage, and further validation would be through long-term and pilot testing. The pre-treatment requirements based on the results we've seen would be somewhere between intermediate and extensive in terms of the normalized flux at bench scale level. And finally, the hollow fiber membranes are actually favorable in terms of flux performance. Their flux was higher than the flat sheet membranes. However, they're still, due to the nature of the configuration, slightly limited in terms of the applied pressure that we can go up to. So this was the last slide from our side. I think Dr. Samer is having some connectivity issue. He told me his computer was frozen. I think maybe we lost him, but he will probably be joining back in a few minutes. So Dr. Ahmed, I'll hand it back over to you if we want to go through any questions or go through the other presentations and then discuss.
Thank you very much, Dareen, for this wonderful presentation.
Thank you.
And any questions for Dareen?
Oh yeah, just want to ask you a very simple question. When you say the hollow fiber and then flaccid, most of your pre-treatment experiment based on the Toray commercial flaccid membrane. So one of the strengths of hollow fiber is you have a less fouling compared to the flaccid, because the hydraulic pressure is less likely occur in the hollow fiber membrane module. So Dareen, it looks like she's frozen, right? She's
I can still hear you, but my camera is frozen. I don't know why.
All right, okay.
So no, I can hear you, Dr. Shah.
All right, that's great. So, do you have any experimental data? Hollow fiber is better than the flaccid, and then pre-treatment, and how it works well? Because you just show me the only pressure tolerance and then some of your data, rather than the comparison of the fouling impact. Do you have any fouling experimental data?
Yes, so correct, Dr. Shan. We're definitely anticipating that the hollow fibers would foul less than the flat sheets due to their configuration, and we would see, obviously similar to other applications like in FO and other testing, that the hollow fibers, we're expecting them to foul less. We still don't have experimental data on these new membranes, only the power density and the flux. But based on the scope and the discussion, that could be definitely something that we're looking into, and we need to compare as well, compared to the flat sheet, because that could help us, like you said, reduce the pre-treatment requirements significantly, and that would then reduce the cost that we would apply in terms of the pre-treatment. But as of now, no data ready, but it's definitely something we're looking at.
All right.
And that is what we believe the main advantage of hollow fiber is, that if you minimize that pre-treatment, I mean, you are just in a very good stage to go to apply better than flat sheets. So, and they're also very compact as well, so it's safe footprint as well. So.
All right. Also,
yes, those are two main advantages of the hollow fiber.
Okay.
The challenge though with the hollow fiber is of course the pressure, and will it, can it take 60 bar or will it collapse? Where flat sheet obviously can take, with the support and material behind it, it can likely take out higher pressure. We know that. So that's the concern with hollow fiber. Can they take the pressure? They certainly can't take it as an internal pressure, but will they collapse, balloon if you put the inside of the fiber at that kind of pressure? But what happens to the structural integrity when you apply the pressure, higher pressure outside?
All right. When I look at your produced water and versus the seawater concentration, and I see your flux is very low, like around 3 to 5 LMH. Yeah. So when you use the produced water, even though it looks like your TDS is 300 milligram per liter, very high osmotic pressure, but looks like it's not really very big pressure you can generate from your flaccid clay membrane. So when you're considering this kind of pressure, actual pressure, and then real operating pressure, so is it really true, like Anil, he mentioned about your pressure may affect the hollow fiber, and then when you're comparing the flaccid and the hollow fiber, even though looks like a very high osmotic pressure difference, so is it possible to generate more than 3 nmH for your flux compared to your flaccid membrane, the hollow fiber, whether it can create more with stable membrane pressure tolerance? Is it possible or not?
Yes, I think at this salinity, the flux for the hollow fibers would probably be higher. One issue we saw with the flat sheets, when you don't have DI on the feed, when the feed is also a saline solution, the effect of ICP and ECP then is great, and that's why the flux is much lower than what we were anticipating. For hollow fibers, we think that it will be less, and the flux that we'll be able to get out of this very high saline draw solution would be probably higher, and that's something that we also need to test. But the main aspect that we think was contributing to this lower flux of the flat sheet than expected is the ICP, that concentration polarization effect, because for the same osmotic gradient or salinity gradient, when we had DI water and the saline solution on the draw, or NaCl on both sides, even if the same salinity gradient was present, the flux would be much lower when you have saline solution on the feed side. So there was some concentration polarization effect that we saw. And we tried to look more into that, but then in terms of evaluating the pre-treatment, as long as the normalized flux would be applied, then that was sufficient enough to evaluate whether there was membrane fouling or not. And the idea of maximizing the flux would then be another aspect that we can look at and compare versus flat sheet and hollow fiber as well.
Yes, the feed solution do impact performance a lot, and I see the model that the DNA had developed as well may show the same thing. I mean, somehow the the effect of the concentration polarization based on the feed water is heavy.
At least for the TFC membranes that we've tested in this experiment.
Thank you.
But I just want to make sure, am I back? Can you guys hear me?
Yes.
Yes, we can. Welcome back.
Okay. As my computer, when this morning it just says it needs to reboot, and in the middle of the meeting it just got disconnected, but I'm connected right now through the phone.
Wow.
Actually, I'm glad the technology is working. So sorry, but I'm familiar with what Darine is having, so it was a good timing. But I have seen the question. So Sean, I think, but ultimately it's really, I think what Darine is saying is rather than the absolute value, for our focus really, it was really the relevant normalized flux compared to one pre-treatment to another. But you're right, actually optimizing the flux and membranes and that stuff, that's, I think it's a different focus would be. Yeah.
Any other questions? Then go ahead, Dr.
No, I just want to make sure that, so I think with the Darine, okay, I mean, when she said the final report, we are, in a way, I mean, if you look at what we have promised in the proposal, I think we have check marked a lot of those actives. So I think Darine and I we might do a quick screening on the hollow fiber membranes, a quick screening of the pre-treatment strategies that we have done. And then we think we are, at this time, we have really, the reason why we really put a lot of effort into this project in 2020, I mean, and with the biocide issues and all of that stuff, and then part of this year, so hopefully by in the middle of this year, we really have put a lot of in-kind contribution towards this project. So I really could not do a lot of more research work on it as it takes time. So we're trying to kind of like initially diverge and now converge in a way. We're really trying to finish up a lot of the experimentation by middle of this year. Hopefully, we feel we have, from our side, really we have addressed most of the requirements of the project. I mean, if we want to do other things, it will be probably doesn't have to be under the umbrella of this project. We could do it something outside of that.
Right. No, I fully agree, Dr. Samer. I think, as you said, there have been a lot that has been done on this project, and from your side, yes, for sure. I mean, I'm very actually pleased with the progress, especially for the pre-treatment part, because this was a challenging. And we were not sure if if we were able to get actual produced water and do the pre-treatment on it and this, and I think that's actually great effort that has been done. And thank you very much, and thank the whole team. Actually, I think that's
it's really the team effort. But no, I mean, I think if you look into it, I think most of the stuff has been done. You're right. So we just, the question that you could keep on doing work. I mean, you could do work for the next 10 years. The question is, it just adds up into cost and effort and that stuff. But I think, like you said, there are the challenges of the money. We will you challenge that, and then you have few things that you could do, and then, but I think we are a good hand. So that's where we are right now. Just that's what the message is. We will do a little bit more data on the hollow fiber, because we think it's an innovation part that UTS gave us. We'll get some data. We will compare it to the flat sheet, but ultimately, and also based on the relevance in a way. But I agree with you. This is like one of the first studies that people have used real produced water and real pretreatment, and from an oil and gas company with a team. So I think it's one of the pioneering type of work in the industry for that. So, but again, it's applied research. I think what we have not done, maybe like what you said, Dr. Ahmed, what we have not done maybe to go deeper into the membrane and characterize the fouling inside the pores and that stuff. But that might be not really part of this project. We will never promise that. Yeah.
Sure, I fully agree, and I think I fully agree with you. And also, I'd like to extend appreciation to also Dr. Shan and his group for also providing the membranes and being so helpful with Dareen with kind of providing the hollow fibers and also the data that they have provided during this testing. So also thanks to Dr. Shan and his group as well. So yeah, I mean,
we should hear from them, Dr. Shan. Yeah, we should hear from Dr. Shan if they have any new data or something on that.
Sure. Yeah. So should we maybe go next to Dr. Shan team and see? Okay, go ahead.
Okay, let me share my screen. Okay, can you see the screen?
Yes.
Great. So, yeah, first of all, I would like to thank the Tamikyu, Ami, and then GWSC, the Samar and his team. So it's very honored to work together with them for last 3 years, 4 years. Yeah, it has been one of my best experience to collaborate with the industry and university. We have a very clear target. We are in charge of the membrane fabrication and then operation from the ConocoPhillips, and Ahmed is very well organized all the necessary progress. So thank you for all your support. And we are very happy to reach to this level of our performance. So today we prepared our presentation mainly for the PRO membrane. Some of them already you know, and then some of them is a little bit of new data we are happy to share. And then my contents are the review papers on PRO process and then membrane development. So we will discuss about what's the current status of the PRO. So what's the commercial opportunity, what's the largest scale in all of around the world, and then how we can catch to the next step of our good experience. Already ConocoPhillips have developed real produced water and hollow fiber flaccid, and then also how we can go next step. So we can discuss together with Ralph. That's our current review paper and perspective, and then our future of the PRO. Also, we have developed the membrane mainly for graphene oxide and shift COF based nanocomposite PRO membrane and sulfonate functionalized porous organic polymer. Also, Ralph he has developed chlorine oxidation. In fact, the bioxide, the ConocoPhillips mentioned about biocide. In fact, I don't know, most of biocide is very much damaged polyamide layer. So it's like a chromium based biocide, or what kind of biocide? In fact, is it Kubota produced biocide from Japan? So it's one of the very interesting, but we utilize the chlorine as one of the technique to improve the overall PRO membrane performance. And then also we have developed the polydopamine interlayer PRO membrane. And then already, in fact, we want to ask you what's the progress of our flaccid and the hollow fiber membrane. And then Dareen already presented, so we want to share this data. So Ralph, you can summarize what we have done so far and then progress.
Okay, good afternoon again. Before I start, I would like to thank this entire group for supporting my PhD study, which I have just completed recently. So thank you for this project. If not for this project, I will not be able to have done my PhD. So for the last 3 years, so last year we have submitted and have this peer review paper published, and this is just a comprehensive history and progress of all aspects of PRO. So from membranes to operation to the actual pilot scale demonstrations, and the various applications of PRO, either as a standalone process or integrated with the other hybrid processes. So I think the main point that this review paper has shown us is that there may be challenges with PRO being a standalone process, but I think it in itself, it can be one of the unit processes for an integrated process, especially for solutions such as produced water. And one of the things that we have included in this review paper is the recent study of ConocoPhillips regarding the different treatment processes which can be done on produced water. So I am actually curious or interested in learning if there are further progress that we can put together regarding PRO and waste produced water treatment. So maybe we can look into that after this this meeting. Then from the UTS side, we have sorry. Sorry. I thought this was my file. Sorry. The next work that we present is Professor Sean. Yes. So this was mentioned by Darine earlier, and this is the first work that we have under this project. So we used GO to be the modifying agent for our PRO membranes. And in this study, the key finding is that GO can definitely improve the performance of the membranes, and it is quite simple and very effective. However, the difference with the performance which we have actually experienced in this project and from this paper, because of the differences in the preparation of the substrate material. So for example, for this particular paper, the maximum pressure tolerance exceeded more than 16 bar. However, for the actual hollow fibers that we have used, for this project and sent to Qatar, we have only around 10 to 11 bar maximum pressure. So we have tried to constantly make the same membranes, but it changes every time, especially for different materials. So we hope that that you didn't have any problem, even though the hollow fiber modules that I've sent have lower pressure tolerance. For our next study is the incorporation of a sheath-based network COF on our TFC membranes. So this sheath-based network is called SNW1, and this was incorporated in the polyamide of TFC membranes. And this was performed on flat sheet, and the maximum pressure was 21 bar. However, because of the thickness of the membrane, so the water permeability was not exactly the optimized water performance, but water flux performance rather. So the power density is a bit lower than what we would have expected. So for this study at 21 bar, we were able to achieve 12.1 watts per square meters. Following up on this, we have another work which incorporated sulfate functionalized porous organic polymer, and this one was better in terms of performance. Again, because learning from our past experiences, we are able to optimize our support material. And this one, slightly lower pressure tolerance at around maximum of 18 bar, but the power density is 14.6 watts per square meters. Then, so basically, all of these three studies focused on the preparation of PRO membranes by modification using nanocomposite materials. And after this, I also performed 2 other studies. First, on chemical modification of PRO membranes. So in this study, chlorine oxidized CFC PRO membrane. So this paper has recently been submitted in GMS, and this was also presented during 2020 ICOM conference in London. So in this study, the key finding is that there are different chlorine oxidation conditions. So the exposure period, solution pH, heating, and these were performed on the TFC membranes to determine the effect on water flux and power generation. So usually we are curious about what is the why do membranes require chlorine resistance? What effect does it have on membranes? So in this study, what I did is maybe it will open up the membranes. Maybe it would provide a little bit of a damage, sort of damage on the membranes, and it can maybe improve or increase the water permeability, and maybe we can control selectivity. And that's what happened in this study. So oxidation was optimized to maximize water permeability while minimizing the effect on selectivity and strength. So after the optimization, we were able to get like 84.7 LMH water flux without any application of pressure. But after application of 5 bar, so this study is was envisioned for lower pressure PRO operations. So for example, if we want our membranes to be operated at, for example, 5 bar, it can give us a power density of 4.7 watts per square meters. And the specific reverse salt flux is around 1.8 grams per liter. So in this study, so we have this particular study is just for lower pressure operation of PRO. So maybe this is something that we can use later on. We are not sure, but it is something worth looking at. Another work that I have done, and this was actually I have sent samples to Khalid last year on polydopamine TFC membranes. So this one is I made an interlayer between the support material and the polyamide, and I put a nanoparticle polydopamine interlayer. So in this study, this was also recently submitted in desalination, and this study showed that the formation of the nanoparticle polydopamine interlayer affected the formation of polyamide, and therefore it would also affect osmotic performance. So the TFC membrane with a nanoparticulate polydopamine layer formed at pH 9. So this is this modification happens at a specific pH, and it exhibited the best initial water flux of around 40.8 LMH, and we experienced really good pressure tolerance of around 25 bar, and the highest power density was 17.1 watts per square meters at this pressure. So this is my last work on PRO membranes for this project. And
thank you, Ralph. And then
and then we also delivered the membranes last year. Before I came to Japan in February, we sent these 2 batches, and Darin has already reported the performance of the hollow fiber membranes. Then later, maybe Khalid will explain or will provide results of the flat sheet membranes. This is the first batch that I sent in February last year. Then in August last year, I also sent the polydopamine TFC membranes. So we can hear more from Khalid.
Yeah. So, just a quick question, Ralph. When you talk about chlorine, actually, I mean, this has been like for the past years, TFC membranes, we know that they are really resistant to free chlorine, but all of the municipal water recycling, they have been really allowing 1 to 2 milligram of combined chloramines. And that has not shown really significant an issue. So I'm building on what you are talking into, also what Dr. Shan also mentioned. He mentioned biocide. Biocide, I mean, they are historically, being used ahead of RO membranes. So what are we saying that ahead of RO, thin film composite RO membranes? So are we saying that the PRO membranes have a different chemistry that could be impacted by chloramines as well as biocides?
I think
we have not.
Okay, just
sorry.
Based on my perspective, in wastewater treatment plant, even any other RO, seawater desalination, because they cannot utilize their chlorine or free chlorine or hypochlorite, cannot utilize the RO membrane, which is the mostly polyamide-based membrane. They are easily damaged by chlorine because they have a very strong oxidation mechanism. So before they go through the RO feed water, they go through the SDS. SDS, the removal of all the free chlorine. So they remove the active chlorine before RO feed water, and then possibly you may not aware of they need the SBS pre-treatment before RO if there is any chlorine disinfection. So any kind of oxidation, even chloramine, what you are saying biocide, that's exactly the Kubota in Japan. They made a patent which can be used for RO bio fouling control biocide. So that's the reason why when you say your biocide, which kind of material, I don't know exactly, but this is a very special. RO cannot tolerate the chlorination at all. Otherwise, this will damage all your polyamide layer. Same as RO and PRO. Both of them.
So just to follow up, that's in wastewater and also in pre-treatment for RO, even for water treatment, they have to do two-step. It's a chlorination and then dechlorination. So they use like sulfides or thiosulfates or stuff like that, or basically sodium sulfide, sodium bisulfide, in order to basically reduce chlorine again to chloride before they introduce the water to the RO unit. But this, when you use chlorine, maybe some other like kind of water industry companies, they use combined chlorine or very weak, basically biocide at maybe it's very small concentrations and also weak one. Usually chloramines are very weak biocides compared to chlorine itself. Maybe that's what they are using in order to avoid, like the step of the dechlorination process. But any oxidant will damage the membrane.
Yeah, but in seawater, and I think in seawater there is a more of a concern. Instead of the chloramines, is the brominated bromine and the brominated byproducts. Those are the ones that are even stronger oxidants. I think who was it? Dr. Benito Marinas have done work on that, and a lot of other people. But in seawater, you're right. I mean, you're right. Whether it's chlorine or bromine or brominated byproducts from chlorine, those are very strong oxidants that impact the membranes. But as an industry, you're right. Chloramines, when you say chlorines, you're right. Free chlorine or chloramines. Chloramines are a much weaker oxidant that have been for years right now. A lot of full-scale plants using them on full-scale plants. Even here in Qatar, the RO plants, they are using, I mean, you need to have some sort of bacteria control or biological control ahead of those membranes. But okay, I think that's a good point, good discussion.
So, thanks, Ralph, and thank you, Dr. Shan, for the progress. I think we have only 10 minutes. I'm not sure if we have time for what Khalid wants to say. But I think what Khalid wants to present is mainly about what we have been facing in terms of not being able to go to high pressure because actually the unit itself that I think when you use the flat sheet membranes. Khalid, do you want to go very quickly in 5 minutes?
Yeah,
just
sure.
quickly, without going much. You don't have to present the result. Go ahead, Dr. Samer, sorry.
Yeah, I agree with you. Let's get Khalid 5 minutes and just focus on maybe he has a question or two, or at least a specific thing. It will be nice to hear what the challenge is. I expected it was the biocide, but apparently not. Apparently it's a high pressure. But you're right. I mean that's the remaining part. But when I talk to Arnie, he is like telling me, I'm not really so. And Dareen also, they're saying, we don't have to go to that high pressure in a way for a lot of applications. But let's, what's.
Yeah. Okay. Thank you, everyone. So I would just give a brief about the progress that we have made so far and the different challenges that we have faced. So our focus of the work was mainly on flat sheet membranes using the SIBA cell.
You want to share the screen?
I mean, yes, we cannot see your screen, Khaled. So.
Sorry? I didn't share.
Yeah, you are not sharing now.
Okay. Let me share the screen.
Like your background. Give me a break. You are in the Maldives or where?
Or in the Caribbean. In the Caribbean.
It's something that I hope for. So.
I think you are. That's a quarantine location for you.
So you can see now my screen. So I will go briefly on the progress that we have made. So at the beginning, our focus is mainly doing the work on the flat sheet membranes using SIBA cell. Once we receive the membranes, we start by doing the normal characterization of the membrane properties, the A, the B, and the S. And in this figure, we show what is the pure water flux and the salt permeability that we get, and the ABS that we are getting for each type of membrane. Unfortunately for us, I think Ralph in his last slide showed the membrane that we got, which was damaged. The membrane was shrinking, so we didn't have the chance to really work on the membrane developed for the work. But we did work on the terrain membranes that he has sent earlier. So this table just to show the comparison for each. Then we started to perform different experiments exploring the different concentrations for the feed and the draw solutions, and we worked it up to a pressure of 15 bar. But pressure of 15 bar was not really the main objective of the project. We aimed it to exceed the 50, which actually we achieved in some of our experiments, but not all. So for some of the experiments, we have been able to reach up to 51 bar, and that was using the FTS CTA membrane. For the terrain membrane, the maximum was around 37 bars, and this is and we obtained the power density that was up to 10 for the terrain membrane. We tried to compare our flux data to the work of Henrik at the different pressures, 10, 20, 30, 42, 51. I'm including here only the points of comparison, and we were close in many of them. However, at the high pressures of 40 and 50, we have seen that our flux is a bit less. Actually, not a bit less, maybe even 40 or 50% less. And accordingly, our power density was also less. We referred that the main difference here is that the support that Henrik was using is totally different from the support that we were doing. And I don't think that with the kind of support we had, we were being able to reach the same fluxes that he got. Because this is the main reason for having higher power density for his work. So apparently we had some challenges with the support itself to enable us to reach high pressures. some other experiments that we did to explore the effect of fluorides, different fluorides, and the feed water, and it was as expected for the different TFC and CTE membrane. But really the heart of the work was later related to the support itself. We looked at the support and for ways to able to enhance our support. So we started to, it is here. The support apparently was a kind of a challenge to enable us to work at high pressure. And the other challenge was working with actual produced water. So all the water that we have produced here was using NaCl. We didn't go to the stage of using actual produced water. In order to be able to manage the challenge for the support, we have started to develop our own supports. Okay, so we tried different supports, like stainless steel mesh, stainless steel blade. We have been able to produce some 3D printed supports as well of different designs and to utilize them. With this kind of supports, we were able to reach the 51 bar that we have indicated earlier. But for previous work, we were able only to reach to the 30s, 35 and so on, but not to exceed that much. The main problem that we were facing that upon increasing the pressure on the broad side, the membrane itself started, we believe, to block the flow on the feed side. And we have noticed that the feed flow is going to die at a certain point and not to have any feed on the other side. So we believe that we need a kind of stronger support to maintain the membrane in place and to enable still the feed flow to flow smoothly. And this is what we have achieved by trying these several supports. With this kind of supports, we have been able to obtain a smooth flow on both sides, on the feed side and the broad side, and we have been able to achieve a higher flux, and accordingly a higher power density was obtained with a steady flow up to 30 bars. This last figure that showed the comparison between the conventional support provided by Sterntek and the redesigned support that we have utilized in our work. So this was the main challenge that we worked on. So apparently the support plays a great role in enabling the whole arsenal of the salinity gradient power, because it maintains the flow on both sides and maintains a high flux. The other challenge that we have is, again, as indicated, it is working mainly with NaCl. So we didn't perform any experimental work with using actual produced water. As Ralph indicated, we got the new membranes in August, so it was in the middle of the pandemic. So we were not really running the labs for any experimental work. And the experimental work and enabling it in the lab was to be crucial to assess the new scent membrane. And this is, I believe, something that we need to work on. With that, I conclude and brief my presentation.
Thank you very much, Khalid. That's, thank you for that. I just want to also elaborate a little bit on what Khalid mentioned. You know, like going to high pressure, I think also one has to be careful because in the beginning of the project, we were thinking that, you know, like, and also reported by El-Malik and his group and other people, that the key is to try to basically manufacture membrane that can withstand high pressure, and then if you go to high pressure, then you can, the pressure usually correlates with the power density, so when you apply high pressure, you get more power from the membrane. And it turned out that this is not the case, because when you apply high pressure, you start to have some effect on the membranes themselves that will greatly affect the property. It will affect the A and B and S, mainly the S. And there was some recent publication. You can go up to their one group that managed to go up to 70 bar actually with certain kind of control of the membrane. They have to get support in the middle of the membrane. It's kind of lab scale that cannot be extended to full scale, but they wanted to see what happens when you increase the pressure too much. And they found that the pressure increase does not correlate at all with the power density increase. And this because the properties of the membrane itself is affected much when you increase the pressure. And there is certain, amount of power that you can produce, no matter how much you increase the pressure. So the optimum pressure with basically with much low than what you expect in terms of, to apply for the salinity of the water that is given. So, for example, when you have a produced water, you expect that, your optimum pressure will go to 50, 60 kind of bars when you deal with 200, like the 200,000 milligrams per liter or something like that, 3 moles or something. But in fact, you find your optimum pressure is in the 20s or in the kind of 30s, and then that's the maximum power density that you can get. And this due to some membrane characteristics that basically is, I don't know if it's a deformation, it could be also concentration polarization. The specific issue that we had with Khalid is when you push the membrane too much from the draw side to the feed side, then the feed channel is blocked. Well, this could be specific to the flat sheet. Maybe if you have a spiral one, you might not, and have a spacer, you might not have the issue because you have support from both sides. But the fact that we have the large cell and, you apply too much pressure, then the feed channel gets blocked. And that's why we actually had to manufacture new supports. And fortunately, the supports worked to give us pressure up to 30 bar and recover high power density from it. But again, the key is the pressure does not correlate with the power density. That's the message that we were able to get.
That's important. That's important, Dr. Ahmed. And I think somehow in one of the publications needs to be factored. Because my question to Khalid's work, okay. So I think a lot of the focus is to be able to do this on the SEPA cell, so that just allows you to do the experiments in the lab, but then how that translates into the full-scale application with the spiral wand or a hollow fiber have its own challenges in a way. But you're right. I mean, I think that when we learned a lot at the beginning, but that's what the research is all about. I mean, you just start with hypotheses. Some of them you improve on, and some of them you say no, they are less. Okay, so what you just said is what I have been hearing also from Arnie and Dareen and the rest of the team as well. So maybe it's not like the more power density, the higher energy that we are. Okay, and there is an optimal actually that we need to worry about for a lot of the application.
Yeah. Right. And also, we know that the flux is somehow given as a function of the pressure or the difference between osmotic pressure and power. But if you can optimize both the pressure and also, or the membrane performance in terms of pressure, but also the flux, because the flux can give you also a good amount of power, because there is usually, it's the two together, the flux and the pressure of the driving force, which is the osmotic pressure difference. So, for example, what Ralph presented about, enhancing the flux with the chlorine treated membranes. I hope that we had a chance to test those, but we didn't. But this also, enhancing the flux could be also key. The other thing that I think we all found out for all teams that, especially the ConocoPhillips team, when they did the analysis with the cost analysis and using the PRO for producing power density might not, or for producing power might not be the best option, but if you combine it with as integrated system with something else, like you had in the paper about oil enhanced oil recovery, or maybe like what they do in Korea, like combination of RO and DRO in a system, so you minimize the losses in terms of, you know, like reducing the power, the efficiencies of the equipment when you go produce the power and then use the power to do something else. If you can just use the mechanical energy directly, I think that's also is a better option when it comes to the DRO application.
Yeah. So Dr. Ahmed, I think, you know, I've seen really the, you know, what Sean and his team have done and what we have done and what you guys have done also. You started with the modeling. I mean, I think a lot of the requirement of this project has been met, or even in many cases exceeded in a way. There are the techno-economic analysis that Elizabeth is working on with the team, that techno-economic modeling. And then Khalid, after he did all of this work, let him use those membranes and do some work. I thought you do have a local produced water also, so you might want to do some testing on that. If you, I'm not sure if you were able to secure some of that. So maybe you could do that as an added redundancy testing in a way. But then with that, we are okay, actually. Is that right? Really, I mean.
Yeah, I mean, I was gonna say that. I mean, for you guys, I mean, for host teams, ConocoPhillips and also Sydney, I think, you know, like you have done enough, and I'd like to thank you both for all the work that you have done. The only thing that I need from you next is when it comes to writing the final report. I mean, we first the publication, the pending publication that we have ongoing, within future ones. And also, you know, when it comes to writing the final report, because this, if we request an extension and this extension might, if the extension is granted, it might be like a year from now, for example, something like that, or like early next year when you start writing the final report. I need your help with this report because we need to put it together as a team, you know, like, because I don't want to come like 8 months from now or something like that, and then, you know, like the project is already done a year ago. So what are you asking about? You know, so
we'd be proactive with this. I really think because because Ralph, if he might be graduating soon, and you know, Dareen, and what we are going to do, I think, from our team by the end of this month, all of the work packages, we are going to put a final report, and we will share it with you from now in a way. Like that will
that's
be
what I would.
What you need to put it all together. And I suggest UTS to do the same, because if Ralph, if he's graduating, might be leaving, so let him put all of the work and give you a draft, be 90% of what you need. So at least you will feel comfortable when you put the final report with your team. You could add, cut and paste, and then you could send it to us. We will review it if there is any more edited. So my recommendation is that we give you something by the end of April or May, so that you feel comfortable you had it. And before any changes, it's difficult for us if we stop working on it for 6 months and then to come back, let's say next year or something. Yeah. While it is fresh, right?
I fully agree, Dr. Samer, and actually I was going to suggest that. Thank you very much for initiating this, because I think we, since we are done with the work, and then it doesn't, you know, like it might be good, like you suggested, Dr. Samer, is to go ahead and have the report prepared. And when it comes to the submission, then we are ready to submit it. And this will give us time to finalize it, and also will not be under the pressure when the timeline comes for the submission. So I fully agree, and I thank you for making this submission. So should we put like a tentative line here, or?
Yeah, like, I think it to also, you're right, even your team actually, before the graduates leave, or before, I hope you got Husnain's, all the other team does.
Well, I don't have really? Anybody now sitting either, they're all gone, you know.
Oh my God, that's, you see, you did not, we should have the meeting last December in a way. Yeah, I think for, what is it, a good time that you have in mind for, would it be after Eid, before Eid, after Eid, maybe end of May, maybe, or what do you think?
End of May would be perfect. So before summer, would this be okay with everybody? Like say, like end of May, we have the. I will send you the template for the report.
Yeah.
And then everybody will put his input, and then let's have the end of May as a deadline for the final input. Is it okay with everybody?
Yeah.
Dr. Sean, is that okay?
I'm fine.
Ralph?
Yeah.
No.
Dari, I want to hear from you. It's easy for me to say.
Yeah, that's fine.
You want, but I want to make sure you are going to lead that effort. But I think I know I've talked with you beforehand, and we were really planning even earlier than that. But end of May seems to be it will be good. So Dr. Ahmed, you will get our deliverable by the end of May.
Okay, that would be great. Thank you too much.
So just a very short comment. So we have progressed very well for our project. We can say that the TRL 224. So next step, yeah, of course, we can prepare our final report, but whether we can translate this technology for the TRL 5 or 6, like already the ConocoPhillips have a real produced water. Also based on our review paper, the hybrid system will be the ideal opportunity for PR application. So we have also hollow fiber pretreatment, all the preliminary result. So whether we can also consider next step of the translation of this technology, even small pilot scale level of the opportunity, whether we can go ahead or we can think about, because we have a best commercial industry partner, and then also Ahmed is the very good level of the project manager. So we are happy to produce the, based on your request, pilot size of the hollow fiber, PRO membrane, even flaccid. So happy to collaborate together. So we can also think about the next step of our collaboration in the future.
Very good point, Dr. Sean. I agree. I think, but that's what we will address hopefully in our reports. Towards the end, we will each of us have to put recommendation of the future. And you're right. I do want to see where are the potential. What is the right pilot? If we want to have a pilot, who is ready to do it? I think the best right now is Toray membranes. So I want to know more really what is the progress of the Korean project or so, because to take it to the field, we need to have the setup of like a pilot equipment and a pilot membrane. So I don't know who is the best ready people to do that, to design. I mean, ConocoPhillips, we are an end user, you guys are universities. So we might need to team up with another entity to facilitate. So I would like to hear your feedback on that, as with your knowledge of what's going on with, Korea, Japan, or something like that. I just don't know who is ready to do that, to have that prototype built.
We will investigate more detail what's the real opportunity for the commercialization, and then we can discuss about who can be membrane fabrication entity can be involved, and then we can make a translation of this technology. So that would be a very good opportunity.
Sure.
That should be for your QNRF project of next year. So Dr. Ahmed and I will follow up on that. But you're right. But we are missing that entity. The three of us are good, but we're limited, right? We need to have that fourth entity that will help get the prototype ready.
That's true. Yeah. And again, like you both said, I think this has been a great teamwork, and I think the spirit is great, and we look forward to continue the collaboration. Not like we don't want to, yes, the project will end, but I think the collaboration will continue among the team members.
Darren, you want a photo? I think we might need exactly, this is a photo. Although we could Photoshop the other photo we have, we could add mask on everybody or something, but it might be like if we could open everybody cameras and have us all, if there is a chance for us to take a COVID-friendly photo.
Yes, that would be very nice. A virtual photo this time. I think Shal was also, she opened her camera, maybe she's still trying to reopen it again.
You don't have
okay,
it.
let me take one. Yeah, so 3, 2, 1. Okay, I'm just saving this one. I think this is good. Yes, so very nice. Okay, so we'll share it with everyone, and thanks for it was a very good update, and enjoyed seeing everyone today, and thank you for the meeting.
That's good.
Thank you. Thank you again. My appreciation, and thank you for the great effort from both ConocoPhillips and also from UPS. I really appreciate your contribution to the project. It has been great collaborative work, and thanks Dr. Samer and Dr. Shan for your leadership, and thanks to all the team for your great contribution. That has been a great effort. Thank you. Thanks so much.
Thank you.
Thank you, Dr. Ahmed.
Thank you, Dr. Ahmed. Thank you.
Yeah. Go ahead, Joel.
Thank you. Thank you very much, everybody.
Thank you. Bye-bye.
Thank you.
All right. Take care, everybody.
Bye.
Bye.
Thanks. Bye. Bye. You all. Bye.